Welcome to the stream, everybody. I apologize for last week. Me and the internet company didn't get along so well, and yeah, so apparently their entire tower went down, and that completely killed everything I'm doing. So that turned into a really fun day. They got it back up and going by that evening, but yeah, the joys of an internet business, right? You do this stuff online, and it is great as long as there is internet and it works. When there's not, kind of hard to do things. Anyway, it would have been a fun birthday stream. I will say that. I was really looking forward to it, but what can I say? With that, I hope you're having a great week. Hope you had a good weekend. Hope your football team you enjoy is doing well, and if it's not, there's next season. Yay? No? Sensitive? Never mind. Um, with that, so far the teams I'm rooting for. So my primary go-tos, one, I'm a college football all the way. I've been following the Aggies since Texas A&M since 2013. Since I've done that. Prior to that, I was heavy into the Cowboys. Got bored of the NFL. Anyway, we're here to talk about chillers. I'm rambling, but I'm back into the Cowboys. As of this season, I decided I'd give the NFL another shot after I really enjoyed the Super Bowl this past year, and so I was like, you know what? Why don't we have fun with it? See how the NFL goes. It's actually gone really well so far this season, so looking forward to that. I do see that the questions coming into the chat, everybody. I do have two questions that came in. I'm going to get to first, and then I will jump straight into the chat questions. One of them came through the CQA portal, the Chiller Questions Answered inside of chilleracademy.com. So if you want to get that, I'm doing my best to keep it as updated as I can. I know I sometimes get a little behind on it. Either way, hope you're having a good week. That's what I was trying to say, and I got sidetracked with football. Hope you're having a good week, good start to your week. And if you're not, let me have your bad one for you. Go make that deal. I do want to point out over here, so I'm not going to make a whole thing of it. I'm just putting it out there. I have a hands-on service training class I'll be doing in Houston. If you are interested in getting enrolled in that class, I've got very limited seats, and a lot of them have already been taken up by just the private pushing outs for everybody a lot of the companies I work with at the academy. Did a touch base with them first. They took up quite a few of those seats already. So if you are interested in that, please send me an email at hvactime@hvactimetx.com, and I can put that here in the chat real quick. So this will be a live hands-on class that we do together in Houston. I will be taking you through service procedures and troubleshooting diagnostics from scroll to centrifugal. We're going to spend a couple of days on that, and then we're going to spend some time actually doing hands-on labs with transferring refrigerants, how to do oil separation, water or moisture cleanup, how to do push-pull recoveries, how to do just various different recovery styles depending on what equipment you have, how you're going to do it, the whole bit. So that'll be the full class. I'll supply all the tools and materials and stuff we need. I just need you to show up with safety gear, really, and I'll give you lunch while we're there. So if that's something you're interested in, it will be in Houston, Texas. Just send me an email, and if there's any seats available, great. I am looking at doing more of these in the future, so if you don't get in on this one, then maybe sometime next year when I get the next one organized, you can maybe get in on that one instead. Anyway, moving on, let's get into our first question. Let me get it set up here. That's wrong. I will say, now this one is good, but when we do post questions, one thing I ask is that we just try to give enough information in the question to where I can easily answer it without a ton of follow-ups. So just something to bear in mind whenever you go to post a question. Just the more information I can have, the better answer I can give, and not having a ton of back and forth. Okay. I have a question about a York YMC squared chiller. The fault is a VSD current overload. I've checked the IGBT boards, checked electrical connections, megged the motor, checked the PRV calibration. Any suggestions? It's always on startup after being off at night. You've done all the right things from a possible drive issue, right? So being a VSD, so that's York talk for VFD. It's the same basic thing. So okay, let me back up a little bit here. For anybody that isn't aware, a lot of our chillers nowadays are on variable speed drives. These drives are used to speed up and slow down the motor in order to better control capacity. We have basic concepts of this in a lot of other facets. It's basically the same thing as if a blower motor is trying to control the static air pressure on a RTU or an air handler system. Like if you're familiar with those types of setups, then our VFD on a centrifugal or just any compressor is basically doing the same thing. We're not trying to control based off static pressure, but we do want to control based off of load. So the more load we have, the faster we need the compressor to run in order to make that load, and yada yada. Now, it gets a little more complicated than that with centrifugals, but it's a high level idea of what we're trying to accomplish there. So all the components mentioned here, IGBT boards, those are your inverters. That's how we send the voltage to the motor to actually vary the motor going up and down. Megging, so that's referring to a megometer check. If you need a basic megger, if you're not familiar with that, and maybe you haven't invested in a good quality one, I do suggest the Klein megger that they make. It has been phenomenal. They may not hold up as long, so I have seen them where depending on how much you use it, they'll crap out within the first year or two of use, but they're inexpensive. That being said, the Fluke versions of them, like I see those hold up extremely well long term, but they're just a lot more money. So you can decide that for yourself. But what that check is doing is actually trying to verify our motor our motor ohms to ground. How strong is the insulation? It's also referred to as an insulation test or a motor insulation test or tester. So that's what we're trying to verify there is the insulation on the motor getting weak? A megger can do that. It's a standard practice to check with a machine. With a high pressure machine, which a YMC squared is, it's a 134A machine. And I think they have been switching to the 513, I think, on those. I don't know that to be true. Either way. With a high pressure machine, you can check it without any problems. Just be cautious if you have a low pressure machine. Do not check it with it in a vacuum, the motor itself. All right, so we check the PRV. So the PRV, that's pre-rotation vane. That also is just an IGV, an inlet guide vane. So if you're, in terms of just transferring terms, if you're familiar with an inlet guide vane, that is your PRV. So if you're not familiar with that at all, your PRV is referencing, that's how we control capacity coming into the compressor. So what it's technically doing on a super technical term, it's actually changing the angle of rotation coming into the impeller. That affects how much energy we can apply to the refrigerant, which affects how much compression is applied, and yada, yada, yada. End of the day, on a very basic level, it's just affecting our capacity, right? So we can increase or decrease capacity. So that does mean on a machine like this, we both have a PRV and a VFD or VSD, that is affecting how much capacity the compressor is using. These two items will work in unison together. So just from a basic rundown of the question, when I see a situation like this, it has almost always been a pull down issue. So these York panels have a pull down setting. It is in the motor menus, or the set point menus. It may be in the set point menus. I don't remember which. I think it's the motor menus. I'd have to pull it up. But either way, there's going to be a setting in there for pulled down. And so what we're wanting to do is actually change that setting, or increase it. Some of them have them turned off, or they're set to 0 minutes. I think you can do where it won't go into a pull down at all. So what happens is when you first come into a startup, I can illustrate this. So when we first come up to startup, let's say we have this. I want to do a graph. Let's try it. We have our water temp. Okay. And no, that's not going to work the way I thought. Let's see. I'm trying to think of how I could illustrate. Maybe I just give up on that. I may be pushing it too far. When we first start up, one of the things the compressor is going to do is it's going to try to stage up to its maximum as fast as possible, because what it wants to do, these machines are built to achieve leaving water set point. That's your LWT. So all it cares about is hitting that set point metric. When it turns on and it sees that we're way above set point, it's going to do everything it can to get capacity up so that we can start to get that set point down. That's all it cares about. Now, if our current limit, so this is it's a value that is monitoring the current percentage, the RLA or the FLA of the compressor, and we know that, okay, this motor is only allowed to run 1,000 amps. But so we're going to set that RLA to 1,000 amps, all right, which would be 100%. That's 100%. Well, what can actually happen is, as the compressor is staging, it's possible for that compressor to increase load on that motor beyond that 1,000 amps. It could increase it to 1,200 amps, which would be very detrimental, could cause a failure. So we have to put that limit in there called a current limit in order to prevent the compressor from overstaging the motor and damaging the motor itself and overdrawing on too many amps. Now that setting is adjustable, so we can also lower that setting to, say, 80%. So part of what happens is, as we stage up, and if we don't have a pull down programmed in, which I very commonly see that a lot of these panels won't, the compressor will go straight to 100%, and it'll get there quickly, which usually causes a little bit of an overshoot, and it'll back off. Now, the OptiView panel does not trip immediately as soon as you get an overcurrent. There is a little bit of a delay to where if it gets over the current limit, which I think is 105% on those machines, if I'm not mistaken, if you get over that for several seconds, I don't remember exactly how long it is, but then you will trip on an overcurrent limit. What is it? You'll trip on a VSD fault for an overcurrent. What I see happen is, when we have a morning startup, we have a lot of load on the loop. It is a very, very heavily loaded loop because it's been sitting stagnant all night. It's been slowly collecting heat. The whole space has gotten hot. Like everything's heated up. So it's going to take some time to get that back down. Now this doesn't always happen, but there will be these windows that of just seasonal or whatever, where when the machine turns on and tries to capture the load, it gets up to 100%, and it's trying its best to float right there at that 100% mark. But let me tell you, 5%, especially with a high load on a centrifugal, is basically nothing in terms of a margin of error that machine will have. So it's spiking, just over 105 to maybe down to below 100, but it having this constant up down pattern in the current draw. And it may not even be that the PRV the PRV or the VSD we're adjusting, those may be stable, but because we have such a high load, you see these current swings with the machine reacting to the water conditions and the very steep drop that is happening on the leaving water temperature. So what I see happen under a high load condition, it's the motor ends up getting pushed just a little too far over that 105% if the current limit is left at 100%, which then causes it to trip out on a current overload. Everything else will be fine. It's not actually a problem with the drive itself or the motor. You did all the right steps there. Don't get me wrong. You did all the right steps in checking each of those items. But I think it's probably just a pull down. So with a pull down, what that setting does is we can tell the system that, okay, at startup, when you see this high load and we're way above leaving water set point, we don't want to go to 100% current limit. We're going to set that a little bit lower. I usually set mine more like 80%, somewhere in there. It takes a little longer for the loop to get under control, but that's okay. Or it's okay on most plants. Let me say it that way. There may be some facilities, you could be this one, where we need to get there faster, but I doubt it, being the fact that your chiller turns off at all. So if it was really that critical of a site, it probably wouldn't even turn off to begin with. So either way, we'll set that current limit, and we can set a timer. Now, different panels do it slightly different ways. York specifically will have a timer on there that, all right, for this time frame, you could do 30 minutes for an example. For the first 30 minutes of operation, we want to have a pull down current limit of 80%. And then after that, then you can go to 100% current limit. Now, it's possible that the machine might not even, by the time you hit that 30-minute mark, it may have already began to drop below the 80%. So you may not even need to stage up further by the time the pull down timer expires. But if you do, the idea is you've pulled the load down enough to where it's staging up higher, 90%, pushing 100%. It's not going to have the same instability that it will when it first goes to turn on for those, let's say, that first quarter of an hour, 15, 20 minutes, where it can be very unstable, and you'll see that your current constantly fluctuates. Like, there's a lot fluctuating, and it's just a load issue at that point. So the pull down timer is meant to account for that, give you a slower coast in period and get you further off of those limits, and then let the machine turn loose and do the rest once things have been settled down a bit. So that would be my suggestion here. See if your pull down settings are configured. If they are, maybe they need to be a little more aggressive. Maybe you need to lower that current limit set point. Maybe you need to extend that pull down time. It could be either or, could be both. That would be that's what I have done in that situation. And that's one of the first things I check whenever I get those alarms, and I know that it's only at startup that it's happening. It's the first thing I look for is, what is my pull down set to? And then I'll adjust that as I feel like I need to for that site, and it has resolved that problem every single time for me. So yeah, that is my suggestion. Uh, yeah, how you doing? So I see everybody doing. Tom, Mike, Tristan. I know quite a few guys. We've got quite a few of JCI's guys are in the Chiller Academy. So um, whether or not they'd be able to do anything for you in terms of um, maybe just answer some questions. I'm not sure what you're needing. Feel free to throw it in the chat. Maybe we may have some here in the chat today. I see a Shrek. How you doing, Familia? Good to see you, bud. I'll get to that question in just a minute, Bubba. And you too, Caleb. Mr. Boone. All right. Let's move on to our next question. Come on. Give me just a minute. Let me get it set up here. Okay. All right. Do all the pipes on the chiller loop, no tower, it's a closed loop, have to be insulated? Even the pipes going into the condenser. I haven't seen any effects to our chiller system or our cooling, but mainly asking for the standing water under the unit on our rooftop. Thanks. Condensers are about 4 foot off the rooftop. So my initial answer, without getting like in the first couple of lines there, would be no. That typically your condenser water does not need to be insulated in most circumstances. Now I say that to say, depending on your environment, right? So if you're in a northern environment, or if you're on the closer to the poles of our hemisphere, depending if you're north or southern hemisphere, either way, if you see harsh winters and you see a lot of freezing conditions, you likely will see your condenser water pipes insulated. You'll also likely be dealing with more glycol systems, or you may just be draining the loop once you get past heating or cooling season. So once you're past the summer heat, you will likely see, most plants, they'll run glycol through part of the early parts of winter when it's still shoulder seasons, and then eventually, unless it's like a processing facility that needs to run year round, they'll drain the loop, right? That's what I'm used to seeing. But in plants that will do a winter shutdown, basically, and you're in those extreme cold environments, they will usually have some form of insulation on the condenser water. Now, like in my environment here in Texas, we're much closer to the equator. No, we rarely insulate the condenser water. It's got to be for a very specific purpose, and it doesn't matter if it's open loop or closed loop at that point. It just rarely gets insulated. It's usually not needed. And when we do get into freezing conditions, it's for short periods of time, and we have heat trace, and we can flow water through the tower. Like we can do things in order to circulate water and keep the tower warm so that nothing freezes, especially on a closed loop. Like with a closed loop system, the classic way we would solve that is we would just turn the pumps on when it got cold, even if the chiller wasn't running, so that we could circulate water. And moving water is hard to freeze. Standing water is where we typically freeze. Now, you say you don't have a tower, but you have a closed loop. So that would make me think you have a ground source. So you either have a ground source cooling, like a geothermal loop, or you're dealing with river water or ocean water, whatever the case may be, for you not to have a tower but have a closed loop system. Specifically, I'm assuming you've got some kind of geothermal loop on your site, and that's what you're going through. Again, it comes back to, depends how worried you are about freezing. In terms of its heating ability, or cooling, how about this? In terms of its cooling ability during normal operation, when we've got a heating load, not worried about it at all. That is not. We want the chill water pipes insulated, because if we don't, they'll just sweat like crazy, and we lose a lot of efficiency, because we want to deliver a very specific water temperature, typically about 45 if we're doing comfort cooling, 44, 45, or if we're doing some kind of processing, it may be 40, 42, or down into the 30s or 20s, depends on what we're trying to do. Maybe we've got a thermal bank we're trying to get an ice slush for, that's going to push you down into the 20s. Regardless, we want to have those insulated on the chill water side where the evaporator is, so that we don't have heat getting into our pipes, losing efficient, because then it's, instead of heat being taken in from the load, now we're just taking heat in from the ambient, and it's just waste heat at that point. It's not actually helping us, and we're having to cool more water in a way that we don't want to, don't need to. Yeah, so that's kind of, it's worded a little weird for me, so that's why I'm struggling with the kind of the second half of it. I mean, being on the roof, I'm assuming it's probably up in a penthouse on the roof. And the condensers are about 4 foot off the top of the roof. Yeah, I'm just I'm trying to make I don't want to miss something in the question and not fully answer it, but at the same time, yeah, I think I'm overthinking it. They don't have to be insulated. Just, they don't. The main benefit to insulating comes back to your winter conditions and time of year, and how you manage freeze protection. That is when we want to think about and worry about insulating. If we're not worried about that, typically not going to be insulated. That's the fastest, most abbreviated answer I have to that. Okay, let's get to Mr. Caleb's question here. All right, can you walk through the refrigerant cooling system for a CVHH with refrigerant cooled oil, motor, and AFD? Also, what is the key difference between a CVHH and other CVH models? Is it just number of stages? Now, I know we've got the ones I can for sure picture exactly off memory is the CVH E, F, and G. The HH, I think, is just the larger, that's just a larger centrifugal. What I'm going to do, I'm going to just verify real quick to make sure I've got the CVHH in my head correctly. Yeah, because I'm pretty sure, yeah, it's just a larger tonnage, if I'm not mistaken. Yeah, so I'll show you. Basically, I just pulled the manual real quick. You can look at it with me. I'm looking at some of the diagrams. I want to see a development sequence. Okay, yeah. So I think that's just a newer, larger. Quit it. We have an economizer. Oh, so this is a single stage. Okay, so I was thinking this was a 3-stage, but this is actually. So this would be the updated version of the CVHF. Before. Let me find the schematic here. So I just want to make sure I want to answer correctly. So let me just look through this together real fast. There should be a schematic in here for the different refrigerant and oil cooling cycles. I just want to find that. Here it is right there. Okay, so we've got, that's going to be oil coming off the pump. So we have a refrigerant pump that's coming in from the drop leg like typical. Comes out. Yeah, it hits our standard cooling ports. We have our 2 drain ports. Those come down back into the condenser like normal. Anything extra going on here that I am not aware of? That's oil feed up, oil return, comes back into the tank. Got our inductor. Those are going to be inductor lines. Comes back. Feeds in. It's a vent. So I do see that they have updated some of these line connections. I do see that. I see our eductor. Looks like it got moved. Or is that? Oh, that's our oil filter. Oh, so this has a different filter block assembly. I see. I haven't seen one of these in the field. But our filter block is up here instead of down on the tank itself. Okay. This is going to be that right there should be a filter. Or you can, not like you can see anything. I'm sorry. All right. Yeah. So now you said specifically you have a, it has the AFD cooling. And you have refrigerant cooled oil, which for those, let me check something here. For those, we typically pass it through the economizer. Oil cooler. Oh, yeah, so right there, number 8, braze plate heat exchanger. I see it. Okay, I do see it. So it doesn't look like the refrigerant pump is feeding that oil cooler, which I'd say is it wouldn't be able to. It'd have to flow. So it'd have a connection from the liquid line going into the cooler and then back out into the evaporator in order to get the saturation down low enough to actually cool the oil. I need to read up on this newer version and get a little more familiar with it. But motor cooling's the same. I see the oil cooler. They're doing the same thing everybody else is doing. Like, this isn't special or unique to Trane in any way that I can see. But I can cover that. And then the AFD, yeah, they're just pulling off. They're flowing the. They should be flowing liquid refrigerant through the AFD to cool it, and then just piping it back into the condenser. If I'm not, just trying to make sure I'm remembering that correctly, because That's a specific package. So basically, that's a like an optional. The AFD cooling is an optional package depending on the drive assembly you have. So the smaller ones will be air cooled, or we could just have a standard starter panel. Those won't have any cooling, and then you get into the AFD panels, which has the refrigerant piped in. I think those do run off of the liquid pump. I think the liquid pump pulls and it pushes into the motor, and then it pushes into the AFD and then flows back into the condenser, which both of them drain back to the condenser. I think that is true. I would have to answer the AFD 100% correct. I would have to reference the material or just go back and look at some of my my pictures of how the piping was done. Either way, we can talk about the rest with confidence. Just, I guess, getting my disclosures out there first. All right. So, what we have our oil tank down here. And then we have our condenser barrel with our economizer drop leg right here. All right, now the economizer and the rest of this is built out further, but just for trying to simplify Trane's graphics here. So right here, we're going to pull off of we're going to have a line pull off the drop leg for the condenser liquid line. And that's going to come into our refrigerant pump. All right, so this pump is then going to feed up to our motor. All right. So our motor is connected to, we have a 2-stage compressor. So we have stage 1 and then stage 2. These, feed multi-stage compressor. If you're not familiar with it, we'd have to cover that separately. This is going into the evap suction, but we have suction gas pulls into stage 1, feeds into stage 2. Stage 2 feeds out into the condenser. Cycle repeats. So per the manual I was just looking at, this is a 2-stage machine. One way we can tell that is based off of the economizer lines. The economizer only has one vapor line coming back into stage 2. The 3-stage machines have, which I think is your CVHG series. E's do as well, but you have 2 lines coming in, right? It's off of the economizer. One will feed into stage 2, one feeds into stage 3, right? So there's different pressure cycles throughout the refrigerant circuit. So that's fastest way to tell how many stages you have with these machines. How many lines do you have coming off the economizer? 1 line, 2-stage. 2 lines, 3-stage. Simple as that. Now, our pump here, get a different color to illustrate, is going to pump that refrigerant up and into a plate here at the motor. And this is a metering plate. Like it has it has a, in the gasket, I remember it having a choke down kind of almost like a flash plate. It's a type of orifice, if I'm not mistaken. So it's not much. We're not dropping this into low pressure ranges or anything, because you got to keep in mind this whole system drains back into the condenser. So we're taking this, we're pumping the liquid up into the motor, but whatever pressure drop is there should be fairly minimal, because ultimately we're coming back into the high pressure side of the system. But then inside of here, let me move my, inside of here we have our stator. Okay, so what this system does, and inside of the stator we have our rotor, right? So we have our bearing, we have a shaft in between going through the stator. Kind of get the picture. We're going to use brown. So as we get up into the stator, this refrigerant is flown all through the stator. And essentially the idea is it flows through, cools the motor down, it comes back out and drains back into the bottom of the motor housing into these two drain ports. And we have one on either side. These come down into a T, and then they drain back into the condenser. So we're pulling liquid off the bottom of the condenser. We're pumping that up into the motor. That liquid flows through the motor, not as a low pressure state, but as a high pressure liquid. And then it comes back into the condenser and just drains back in, gets reprocessed back through the rest of the liquid in the condenser. It's not flashing off or anything. And then it just kind of creates this repetitive cycle. Now, if memory serves on the AFD, now the AFD would be mounted on the back side of the motor here. So when I'm going to do those, I'm going to draw it over here just for illustrative purposes. So the AFD, man, I don't want this to get confusing, but I don't. Okay, the AFD, just imagine this is sitting here, but we have this would be the back side of it. We have refrigerant hook connections on the back that there should be a line that comes off. And if we do have a train tech, please feel free to correct me here. I'm trying my best to do this from memory, and I don't want to missteer this, but anyway, this line has up here, there should be a T that comes off and feeds into the AFD panel, and then it'll push back out and come back into the condenser. I'm pretty confident that's how Trane is routing these lines, and the refrigerant pump is pumping through this panel. And so its whole goal is our liquid refrigerant is cold enough compared to our electronics that it's not a problem. And we don't, so here's something key to know about when we do something like this. These electronics, we want them to float in the low hundreds, low to mid hundreds in terms of temperature. So we're talking, 100 degrees to 120, 130, 40, somewhere in there, right? That's the kind of basic range that most machines are trying to maintain their drive components at. And it's a healthy operating temperature. It's not too high. It's not too low. We're not going to be worried about condensation, which is why we don't use any low pressure on panels like this. The only compressor that does that that I'm aware of is the turbo core. The turbo cores will go through a flash plate. They do flash that refrigerant off, and it will cool as it goes through the electronics cabinet and all. But it's done in just the right way to where they don't have condensation issues, and they're not causing their components to get too cold and start to get wet and things of that nature. But that is one of the concerns we have with these other styles of panels. If we did try to send low pressure, low temperature refrigerant through here, we do risk condensating. So by flowing liquid refrigerant, we can just have this continuous steady stream of cooling going through the system, not having issues. Same thing we do on the York side. Instead of it being refrigerant based, we do a glycol solution. We call it an inhibitor, or York does. And they use that inhibitor to flow basically a glycol loop and cool that down. And then we use condenser water to cool that glycol loop down as independent circuits from the condenser water, but we're not using refrigerant. That's on the York side. So for Trane, they're using refrigerant cooled panels, and I think, if memory serves, they are coming off of the liquid pump line to do that. Now, the oil cooler should be getting fed. It should be coming off of, have a liquid line fed to it and a metering device, but it will be going through a change. So What I mean by change is a pressure change from low to high, or from high pressure to low pressure. So with our cooler, it's going to be, it's say sitting off to the side up here. We're going to have, coming off of our oil pump, we're going to have one line feeds up in and then back out of the cooler and then feeds to our bearing assemblies. All right, so this comes over here, here, and then feeds up into, or technically up to the top, feeds in up here for the bearing, and then this one feeds here. Either way, you get the basic picture. Thrust bearing, journal bearing. So that's the oil side, but our refrigerant is going to pull, let me use this one. It's going to pull off of the liquid line, and it's going to come up and feed through a metering device into the cooler, and then from there we will flash off back out of the cooler and into our evaporator. So this way we get the braze plate circuit cold enough to actually cool the oil, because historically, before they used this style, they would actually route this line through the economizer, and there was a heat exchanger in the bottom of the economizer, and the oil flowed through that heat exchanger in order to cool the circuit. Now, one of the things about that is there were limitations on how much that oil could be cooled and maintaining that oil temperature. So one of the benefits of using a braze plate like this, in my opinion, would be we can achieve better oil control. And especially with the newer refrigerants, that is an issue we are seeing, or that I've heard about at least. These machines are having a lot of bearing issues, and it might, my estimation with, they made this change because they're trying to make an adjustment in order to get either a lower oil temperature than what the economizer style of this was able to do previously. I don't know this for a fact. I'm just understanding the design of these machines. I'm taking a educated assessment. So maybe they found that if they ran the oil at cooler temperatures, it performed better in the bearings with the modern refrigerants, or they just needed more precise control. So with these, that metering devices, most of them will act just like they're typically a style of TXV. A lot of them, maybe Trane is going with an EXV style here, but I kind of doubt it. They're probably just using a standard TXV style, which will mean that it'll have a sensing bulb coming off, and it'll be mounted to the refrigerant leaving line of the cooler, and it will modulate its flow based off of that. So if the basically suction line coming off of the top of the oil cooler is getting hot, we have hot oil, then we need to open the valve up more, get more refrigerant in there, cool the oil down. The oil starts to get too cool, then we can close the valve down and allow the oil to come back up, and we can maintain a much more consistent, steady oil temperature with this method, which previous methods Trane has used did not allow for that. And I think that they may have determined that was part of some of their bearing issues that they were dealing with at the time. Again, that is speculation. I cannot say that is 100% true. But this would be how I would expect that oil circuit to be configured, even though they don't spell it out for us, at least in that one particular diagram. Maybe, let me see, maybe they give a more specific breakdown deeper in. I kind of doubt it. I really kind of doubt it. And I may be able to read through this manual. They may visually, or not visually, they may verbally explain it. This would be something I can work on. Maybe I'll do a follow-up on. That might be a fun thing for the next stream, is do a follow-up on the oil cooling circuit. We may just read it here. I wonder, would y'all be interested in that? Let's see. Schematic diagram. Compressor oil is pumped from the oil tank by the pump motor located within the tank through the oil pressure regulating valve designed to maintain that oil pressure 20 to 24. Okay, so they increased oil pressure a little bit. That used to be 18 to 22. Now it's 20 to 24. That's an interesting note. That's a change from older versions. It is then filtered and sent to a brazed plate heat exchanger oil cooler located above the oil tank on the compressor motor circuit. From the bearings, the oil drains back to the oil tank. Be sure to lubricate. That's talking about the heater. Operating temperature 1 to 140. That's the same. That hadn't really changed much. It used to be, I think it used to say like 90, 91, 95, something like that. So 100 degrees, I guess, is slightly higher than with the original. But I rarely ran these machines with the oil below 100 degrees. Eductor, a dual eductor. Okay, so that they may have made a change to that piece of it. Let me see if there is a description of the oil cooler. Here, system. If I'm getting way off in the weeds, y'all are welcome to tell me. I'm just curious at this point. We're just hanging out, right? Flash tank, second stage, all remain. Economizer, baffles. Refrigerant passes through. The economizer reduces requirement. First, notice that the liquid flashes off because pressure drop, orifice plate. There is no mention of the oil cooling circuit. Okay, so they don't mention, in this particular one at least, how the oil circuit is piped. They just reference that it exists based off of how everybody else does it. This is what I would expect. Some version of this. Maybe it's not perfectly. Maybe they're not coming off the drop leg. I would doubt it. I would imagine that they are. But maybe they're pulling off of the bottom of the condenser somewhere, right? That could be an alternative way that they're doing this. I would expect this return line to pipe into the top of the evaporator somewhere. Have a line just kind of stabbed into the top side of it. But to that point, this metering device is going to be calibrated to maintain that 1 to 140 range, which I would argue is probably calibrated more to that 120, 110 to 120 is more than likely what this metering device is going to be tuned to. So let's say its hard set point is 115, 120 with a plus minus 10 degree variance, right? That would be a very reasonable expectation I would have for that metering device to adjust and fluctuate to in order to maintain a very specific oil temperature. I think this is a good update, by the way. I like this change. It adds some complexity to the machine, but overall, I think it's a better oil management side of the system, and I welcome it personally. I think that's a good direction for Trane to make that kind of a change. Hopefully that answers questions in some regard. If not, feel free to follow up further if I just went way off on a tangent that was not useful for you. Either way, I like the question. That was fun. Would you recommend... So getting to Familia's question, Mr. Sanchez. Would you recommend a small HVAC company to service chillers? Would I recommend one? Yes. Do I have one to recommend? Not necessarily, but would I recommend one? I mean, yeah. I think it depends on the machine you have. And I could get off on a spill if I'm not careful with your question. Do you mean would I in general? If I would, I do have some parameters as to when I would and why that I think would be worth discussing. If you mean, do I have somebody specific I do recommend? I don't have that, and that comes back to where you are and whatnot. But yeah, I just don't want to go overkill on the question. So do you mean would I actually just say, yeah, you go hire a smaller company, and then like there are some parameters to that. I wouldn't do that for just any site. Let's see. I guess maybe what the chiller work is like at an OEM versus non-OEM shop. That's what I'm most curious about. Supposedly I've only brushed tubes, never any real troubleshooting. We need Jason in the chat. Where's Jason at? So Jason could tell you from a Daikin perspective. 514A. And an open shop. I think the big advantage OEM guys have is factory support for equipment, troubleshooting, training. Yeah, and I would also add that yeah, Tristan, I would add to Frylock's response of they do obviously they're going to spend a lot more time on their equipment. It's not that they don't service equipment outside of their brand. So like you will probably work on machines. You will very likely work on machines that are not York. You will very likely work on some trains. You will very likely work on some carriers. Like expect that to some degree. But the vast majority of what I would say you could expect to see is going to be York-based machines, and so you'll be very specialized in those for sure. And for some people, they prefer that. Yeah, I fall on the other side of it, which has always been a struggle with me working for an OEM. Is I don't like to niche that hard. Like I like to niche into chillers. Don't get me wrong, but niche into just one specific brand. But there's benefits to that because, like in my case, it's hard for me to keep up with every little detail about chillers because there's just so many. There's so much. When you really specialize for an OEM or something to that regard, you can like crazy hyper focus your understanding of how those machines work and keep up with all their little nuances in a way that would be hard for somebody like me to do who's trying to work on just more of them. So there's benefits, but there's also drawbacks. You know, when you hyper specialize, as long as you're in a position where that specialty is needed, then you're golden. But if you fall into a place where you want to leave and go somewhere else at some point, but you don't know as much about those other machines because you went so hardcore on the OEM ones you worked for, that becomes your next hurdle. It's like, okay, well now you have to relearn these other machines, but you're starting that cycle over. And that has been something I've ran into with technicians. You know, they in interviews and stuff, I've had people fall into that trap. It's just what you really want to do though. That's just my point being, that's something that you could expect to have with that experience. You're going to see a lot of York machines, obviously. But you're still going to work on a little bit of everything. Like you're still going to have the maintenance contracts, and York in particular has been on a kick for several years now, where they've really been pushing these 5-year extended contracts. They've taken several accounts from me because their normal warranty, the customer was not hard locked in to using JCI. But then JCI would come in as their normal warranty was expiring, and they would offer this 5-year extended deal. The trick was you could only use JCI service. And it was a good deal. Don't get me wrong. It was smart on JCI's part. What that also meant, though, is JCI was now responsible for all the maintenance, everything for that machine, which is probably perfectly fine for them. It was their way of getting more work, more market share for their team. But just putting it out there, they've had these campaigns going for a number of years now, and they're still doing it, where you're going to have a lot of maintenance work and stuff just from from those sales pitches that they're giving. And yeah, so just some things that I would tend to expect. Now on the 514A, that is the new low pressure. And I'm struggling with getting these so mixed up. Yeah, 514, but yeah, the 123 replacement. Right. Yeah, so 514 is Kumar is a low pressure is a low pressure refrigerant, meaning that we operate below atmosphere. So there are there's the way we categorize this is in one of two camps. We have high pressure and low pressure. So our high pressures. So the way we describe this is a above atmosphere atmosphere. Okay, so these are your 134A, R22, if there's any of those still around. There are. R22, we have our 513 fits in that category. What other refrigerants have we used recently? I mean, you could put like what R12 and whatnot in there, but yeah, the vast majority of anything produced in the last 20 years is going to be 134 and 513. And then we have our low pressures. So our low pressure means it operates below atmosphere. All right, so these are your 514s, your 123s, and 11s. Those are, well, I guess you've also got the 1233 ZDE or EDZ or whatever the hell. The 1233 that York is using is another one. So these two are the two new ones that are being used. This has been phased out a long time ago. 123 replaced 11, just like R22 replaced 12. But then 134 replaced 22, and then now 513 is replacing 134. So in this case, 123 replaced 11, and then 514 and 1233 are replacing 123. A lot of manufacturers, I say a lot, let's see. I know Trane has gone 514. York has gone 1233. Actually, I think York has done. Have they done both on the low pressure side? I don't remember. I am curious. I want to look up. I'm getting off in the weeds. I don't need to go. That's not what he asked. Reel it in. Daikin, I think, has gone 514 on their WMT. That's their new low pressure centrifugal they've come out with. I think they went 514. I'm pretty confident. I'd have to look it up, but I'm pretty sure that's correct. So anyway, this is how we're describing it, and what we mean is, so on low pressures, the evaporator for sure will be below atmospheric pressure, and so we're talking -6 to -8 psig type of operating pressures. Whereas, the high pressures are just above atmospheric, right? So they're 40 something, 50 something psig, just depending on the refrigerant. I'd have to look up what 513 runs at as a normal evaporator, which I guess we could do, right? So we could pull up Danfoss's ref tool. Really love this app. Highly recommend it. So yeah, 134A at a saturation of say 42 degrees. We're looking at 37 psig. We kick over to 513 and a 42 2-degree saturation would be 42 psig. That tracks very closely. So just kind of give you an idea that these would be considered high pressure refrigerants. They're not significantly above, but they are above atmospheric pressure, and they do not operate below atmospheric, where low pressure machines do. That's also why they have a purge unit installed, because we have to be able to manage non-condensables when there's leaks. High pressures don't have to worry about that, because if there's a leak, the refrigerant pushes out. But with low pressure, we draw atmosphere in most circumstances, unless the machine is online and the leak is on the condenser side. So with these, the condensers can run a couple of psi, 5 psi, 8 psi maybe in some cases on the condenser. But again, it's just a few psi because these are going to be designed that, like, their high pressure tripping is say like 10, 12 psi, and they've got a burst. The pressure relief is calibrated for 15 on most of these. So you're not going to get a whole lot of head pressure with a low pressure machine compared to what you see with a high pressure, right? That's your main differences, and that's how 514 kind of falls into that category. Can a lack of refrigerant be the cause of a high discharge superheat? Considering that the suction gas are supposed to cool the compressor. Yeah, let's get this up so everybody can see. Go. Okay. And this is for Mr. Pilot. Okay. Can a lack of refrigerant be the cause of a high discharge superheat, considering that the suction gas are supposed to cool the compressor motor? Yes, a low charge would. Now, there's things to that. So we would expect to see a high suction superheat at that point. So if it is because of a low charge that we think our discharge superheat is high, then we expect to see our suction superheat elevated as well. And that's going to come back to the particular machine and compressor. So knowing what style of compressor you have is a key fact here, because different compressors operate different ways. So if we're looking at this from a screw or centrifugal perspective, starting off with a screw, it will be more simple, right? So a screw, less load, lower superheat. Pretty straightforward, right? Less load on the motor specifically and on the compressor. So the suction superheat on a screw could be anywhere from, we run them as low as 4 degrees suction superheat, as high as, say 12 degrees suction superheat, even though I really don't like going above 8. Like, I'd much rather try to run 8 degrees on the upper end and 4 degrees on the lower end. That seems to be a very good range for these compressors, but that depends on your application. It depends on a lot. 4 to 12 is technically the standard. So if we start to see us pushing above that, so if I had a RTAA, for example, that wants to run a 4 degree suction superheat, and I start to see it run 6, 8, 10 degrees, I know I've got a problem. Something is not right. I can't get my superheat down. Flip that to a YCIV. Now these are chiller models, all right? So if you don't know what I'm referencing, it's okay. They're just different models. They have different parameters. These are things that you'll learn with time and experience and reading the manuals. So with a YCIV, those want to see 8 to 10. So if I have it, the set point set to 8 degrees, but all of a sudden I'm seeing 14, 15 degrees, I've got a problem. Or 12 to 15, even though my set point is 8 for my superheat on those. I've got a problem, right? Those are elevated superheats. That's going to cause elevated discharge superheats at the same time. And a low charge will absolutely cause that symptom. There are other factors at play, though. So if we get into a centrifugal application, if it's a constant speed centrifugal, the less load we have, the higher the discharge superheat will be. And this gets into how the compressor is able to cool itself, and we could kind of get off into a rabbit trail there pretty quickly. The constant speed centrifugals, yes, lower load, meaning our inlet guide vanes are closing off more. We're putting less cooling through the motor. Even though our refrigerant charge may be fine, we're allowing less refrigerant to pass through. That is going to cause higher discharge superheats. That's different with variable speed. We can actually see those superheats decrease because we're slowing the motor down specifically. But in a scenario where as the centrifugal loads up, if refrigerant and everything is good, then we see that discharge superheat go down as we put more load on it. Again, variable speed centrifugals are different because we are adjusting the actual motor's speed and amount of friction and everything else happening by adjusting the RPM. But a constant speed centrifugal, as we put more refrigerant through it, the lower our discharge superheat will be. And it has nothing to do with the charge at that point affecting it. Now, a low charge in a centrifugal machine will absolutely cause even higher discharge superheats, to the point where if we have a really low charge and then we have to unload that machine very heavily, you're going to see a discharge superheat through the freaking roof on that machine, because we're already limiting the cooling through the compressor, but then we have a low charge reducing cooling even further. Discharge superheat is going to react accordingly. But just be cautious of which compressor you're looking at and what the expectation should be for that discharge superheat based off that compressor and its normal characteristics. That's my main point. Depending on, yeah. See, Mike, the Frylock, Michael, he was already on that. Good job. What is the lifespan of the mechanical parts in a screw compressor, as well as the oil filter? It's a very, very fair question. What is the lifespan of the mechanical parts of the screw compressor, as well as the oil and oil filter? Extremely dependent. Extremely dependent. A perfect machine that has excellent maintenance, proper oil changes, and good refrigerant charge all the way through, has a stable load that's not constantly fluctuating like crazy. Like in a perfect scenario, with good maintenance, these compressors can run without ever needing to be replaced and very minimal service, not even the oil filter done. You can get 20 plus years out of these things, genuinely. But all those other factors are going to depend on how much life you actually have. So I can talk through each of those some. A low charge is going to put a lot of extra stress on the compressor, especially from a cooling perspective, because most screw compressors cool through their suction cooling and discharge superheat. That's their oil cooling process as well. And so what that looks like is when we start running a high suction superheat, or the motor starts running hot, we don't have enough cooling. Maybe it's got liquid injection, but we don't have enough liquid in the system to properly keep everything up. That ends up causing elevated oil temperatures. That is the thing that's going to break down the oil, is high temperatures. That's the first thing that we lose control of many times, and it gets away from us. So we have to keep our oil temperatures under control. Otherwise, that's when they start to turn dark and have a different color. They may not even be acidic. The oil itself is just breaking down from the heat of operation. So, yeah, that could be a charge issue. High or dirty, if you have an air-cooled system or even water-cooled, dirty condenser. Doesn't matter which style, water or air. Dirty condensers elevate head pressures. Elevated head pressures put more stress on the motor. So that's going to cause higher amp draws because we have a higher compression ratio. That's also going to cause more heat to stack because we're trying to compress the refrigerant harder. That's going to generate more heat of compression. And what does that also do? Elevate oil temperatures. These things these things work in unison together. So we have to account for that. Those things reduce compressor life. They reduce oil life. So let's see. Yeah. Dirty condenser, low charge, unstable loads. Now these compressors can load up and down all day. They're fine with that, but that does add a lot of mechanical wear. It puts extra stress on the system if they're constantly staging up, staging down, staging up, staging down. And it's not even necessarily a turning off and on, because short cycling is its own issue all in and of itself, where we're actually constantly causing a compressor to turn off and turn on. That's not good. But even just in the staging up and down process, like every time we have to load the compressor up, like that is putting mechanical stress and wear on the bearing assembly, on the motor, on the slide valve. All of that affects the lifespan of the system. And any stress we put mechanically on the compressor, that also means stress on the oil. The oil is completely dependent upon how we treat the compressor. So there could be situations where you may only get a few years. And what you're looking for with the oil, it may not even be shavings. Shavings are their whole issue in and of themselves, where you've got actual metal from the bearings or the screws or the housing or something is grinding to the point of getting flakes. Compressor's not looking too hot at that point. But the oil itself could just start to look brown and deteriorated. And here's the thing that typically happens. See, I've seen this so much where the oil is not properly maintained. It's not kept up with in the service cycle. It's not being paid attention to. And so the compressor ends up getting to run for sometimes years with bad oil. Because a couple of things happen. One, the oil will start to turn color. It may start to get a smell to it. It may not even be acidic. It just has this off smell. It doesn't smell right. And it will lose viscosity, meaning that it will get super, super thin. And that thinness reduces its lubricating ability. Like the oil is just breaking down back into its base components. It's not holding together in its molecular bonds, which is what's literally happening, like from the heat and the wear and everything. The oil as a compound is breaking down from that into its original elements, and those in and of themselves are not very lubricative, right? They're not what we need for the bearing. So that bad oil, over a period of time, higher mechanical stress and wear, bad bearings, right? That's the effect of that. Whereas if we took care of that oil sooner and we just changed it out, we noticed that it was getting dark, getting miscolored. Excuse me. And if you're doing routine oil checks on maintenances, then these are things you should be seeing as part of that check. When you take that oil sample and you look at it, you'll be able to see, does it look fairly kind of clear? It's okay to be a little yellowish, things of that nature. That's fine. But if it starts to look amber, like a really good beer, and I say good beer, light beer, no, that's it. Good oil may look like mediocre light beer, but bad oil will look like a good beer, right? That's a metric we can look like. And I'm a dark beer guy, okay, so fine. But that's what we're trying to check. If you see that and you don't then take steps to correct that oil, yeah, your compressor has a very short life, or shorter life at that point, because it's just a matter of time. And the oil filters, typically what gets the oil filters is either metal shavings, or if your oil separator has a screen or something in it, that screen material may come out and gets hung up in the oil filter. Like, so there's different ways the oil filter can get plugged up. The most common I see is usually the oil breaking down, and then that causing mechanical wear, and that mechanical wear is then little metal shavings and flakes and whatever it's getting, the junk that's getting in the oil is then getting caught in the filter. And so that's where you see the filter get plugged up. And in my experience, usually by the time I'm having to replace the oil filter, I'm usually needing to change out the oil with it, because whatever was in the oil to plug the filter needs to come out with replacing that oil, right? Those things for me go in hand. If I need a new filter, I probably need new oil. That's the way my mind works around that. So in terms of lifespan, there's not a distinct answer. You do all those things correctly, long life. You do any of them poorly, not so much. Hopefully that straightforward enough. Application on Play Store. So I am, in terms of Chiller Academy, I have plans. There will be a actual mobile app eventually. So I haven't got it developed yet. It's not necessarily right around the corner either, but it is a definite item on the list that I'm trying to work on. It's not a simple process at all, and it will, for me, it will require having a proper developer, somebody who can come in and code it, connect all the APIs, and like there's a lot of technical jargon on the back end of just how code and technology works. So I'll be super excited when I do get it launched. Believe me, I'll let you know, but not just yet. And we're still working on it. Yeah. How you doing, Sterling? Good to see you, bud. Good to see you, man. Do you have a procedure to start up the DX units? York DCH600. Startup, commissioning and startup. I don't. No, not on those. I don't have anything. Most everything I've got right now that I've built material wise is focused around just chillers, air cooled and water cooled. That is something. Okay, let me post a question here. I'm not in a place to do it right now, but like I have ideas and ways that I could do exactly what I'm doing through Chiller Academy, but expand it into general commercial, where instead of being hyper focused on chiller and hydronics, it would be more of the DX side. And so that would be a major distinction I could make with that is, sinuses, is having basically the Chiller Academy with its current version would be hydronics focused, and then I would have another commercial, and not necessarily like low temp rack style commercial, but just regular comfort cooling, standard processes, data center type systems, uh, for like the DX side. That's an idea I have. What would be the interest or the benefit from y'all's perspective on trying to go that path? Now, again, we're talking about a long term path here, but this is like, that is definitely something I have on the table. In addition to the VRF side of this, I know I haven't done much VRF related in a long time, but like the VRF program is still very much on the table for me. I just haven't moved forward with it. So I'm curious to your feedback. Like, what do y'all think? Missed last week, but I think. Oh yeah, so Sterling, last week didn't happen. My internet provider decided that it wasn't going to work that morning, so they didn't. So the way my internet here at my house works, I've got a, because I'm out in the sticks, so I've got a little like satellite dish that sends it to a tower that is over by my fire department, and then that tower communicates back to like the main network servers, and that's how I get internet here, because we don't have wired LAN or any of that here. So and I've thought about going with Starlink a lot, but talking to everybody that has Starlink, like many of the same gripes I have with my local internet service here, they just have a different version of the same thing with Starlink currently, right? So anyway, point being, their tower went down last week. They didn't get it back up till later in the day. I ended up having to just cancel the stream because they were not going to get it back online in a reasonable time frame. They couldn't even give me a time frame, so it just turned back on all of a sudden, and everything went back to working. So yeah, there wasn't a stream last week, sadly. I was actually quite disappointed. I was looking forward to it, but yeah, is what it is. Life, right? Can't control everything. So the current question I have on the table is, like, even just a high level yes, no to your thoughts on, a DX version of Chiller Academy, or even the continuing with the VRF version of this. That is something that, like, your feedback matters to me. I'm doing this for y'all, for the industry as a whole. And if y'all aren't, like, if we don't feel that it's needed, like if all of us as a collective don't feel that we need that type of training the same way we do for the chiller side, I get it. I'm down for it. I can focus on other things. But I do need your feedback to help me understand that, so I'm not just looking at things through my lens only. Must be all the firings in the tech. All right. That's the crazy thing. People just do not understand these. Like, think about this. Without hydronics and what we're doing in chillers, the internet as we know it today, and this whole AI revolution, it doesn't exist. Like, DX systems, from what I have seen, do not support large data centers that are needing to be built and that are being built to support the modern internet. So when we're talking about a Liebert DX system with its own compressor, remote condenser, whatever, they're just not able. The size of the cooling system, it just takes up too much floor space, and it cannot maintain reliably that level of load. Whereas with a hydronic system, we've got systems here in Austin going in where it's 48 chillers for one site. 500-ton air cooled for one site, and we've got multiples of those happening. So a dozen of those chillers could go down, but as long as we can still flow water and we can make some chillers work, we can still provide cooling, and all the crack units down in the space on the data floor are still able to fully function, right? So, and not to mention, like, water is just a way better heat carrier than refrigerant. It just is. I think I saw somebody post a calculation where water is like 4 times as efficient as refrigerant of BTUs per pound, right? Something like that. Now, I haven't actually looked that up to verify that for myself. It was just an interesting factoid that, if true, is like, okay, well, that's amazing, right? Our internet doesn't work without what we do. Like, our whole internet infrastructure literally just turns off, or it's just not possible because we have to throttle it so much because we don't have the ability to cool the equipment properly to have the throughput through it that we do to make everything we call the modern internet possible. Like, it just, I really wish people understood this better. Anyway, me and my tangents reminds me, I've been told there's a few things taking the data centers by storm called liquid cooling. Some like that they actually run the chilled water in tube over the server. Yes, not a crack, right? Like we're used to. Yes, I've seen these. Let me rephrase. I've seen examples of these. I've not personally worked on those systems myself. That's what I mean by I've seen this. So, yeah, and what they're doing is they're flowing it's a non-conductive solution that they're putting into the vats for cooling. And what I would expect that to do is we'd probably end up with 2 loops. We'd probably have one loop separated via a heat exchanger where we ran our chilled water for the cooling systems. We'd have another loop where we would run the fluid that goes through the server vats, as you might call them, that we're processing through, right? And I could see that we would use a heat exchanger to separate the 2 loops. They have independent needs, so that way we're not, like, it would probably be just cheaper, cleaner, simple, easier, all the things to have them separated. So that would be my expectation with a plant like that, is we would use heat exchangers to isolate the 2. But then, yeah, from a cooling perspective, if you can submerge the server, well, yeah, it's gonna do way better thermal, like have a way better thermal profile. Like, to me, it's obvious. Like, having it liquid submerged is just more efficient heat transfer than having it air over or something to that effect. I think it's just a way more efficient system. So I'm down for it. I'm absolutely down for it. I think it'd be really cool. And we still, like, for us, what changes is just we're going through a heat exchanger instead of going through a crack unit in the rack. That's really what changes for us, you know? Other than that, we're still maintaining the same thing. Server rack doors that are actual heat exchangers. Yeah. Quick connect fittings and valves so they can be isolated and worked on with minimal downtime. Yeah, so that's pretty cool. Yeah, that's really cool. I like that. Yeah, that's the thing. You know, I do plan to do a specialized training at some point, or a course or something on data centers. Yeah, heat to use. I know. I'm sorry. So data centers have become they're such a major point for us, and I think they're going to be, like, we may have less manufacturing to some scale, right? We don't know what's going to happen with manufacturing, but what we do know is that we're going to have a tremendous amount of internet compute required in order to sustain the world that is being built. So for that to be true, there's the volume of data centers being constructed and all the, like, it's just, they're going to need major support from us. That also means that we've got to be prepared to service those machines, those loops, those thermal banks. Like, there's a lot of extra complexity and specialized things that go into those loops that make them unique in their own way. That being true, I think we need to make sure that we're properly educating ourselves and we're prepared to work on those systems. And they're not always so obvious. There's things about electronics that if you haven't worked on a data room before, like humidity control is crucial. I mean, crucial, because you get too little humidity, you cause extreme static, and you'll end up frying entire racks in the servers because a static charge sets off somewhere, and it literally just shuts down the entire rack. And then depending on the system, that could be millions of dollars worth of loss between not only replacing the equipment, but the bandwidth that they lost by having that rack offline. Now they can't push as much bandwidth through the facility, which affects their margins. But at the same time, you can't go too high on the humidity because then you start to cause corrosion. And so then we could either have sweating issues in some cases, or we're just going to start to allow a lot of corrosion on the electronics, and the circuit boards themselves are going to suffer for that. And it's going to interfere with the pathways, all the stuff, right? So it's a very delicate balance. So that's another, like, in terms of just courses and trainings and things that eventually, I've got enough on the table at the moment, but eventually I could see being very helpful to, it's just that we don't learn this stuff anywhere else, right? There's not a school we can go to. There's nothing else training wise around data centers and hydronic equipment and all the things we need to know to properly maintain those sites. So anyway, again, that's another what are your thoughts questions, right? Do you think that would be a valuable thing to have at some point? A course dedicated to data centers, server rooms, and maintaining that equipment, especially from a chill water perspective. We can consider as a package unit as classified by York at the website. Yeah. I have 3 Chinese York chillers, air-cooled condenser. When I turn them off, I notice that the pressure is in one of them are equal, but higher than the other values in the rest. Okay, so notice the pressures in one of them are equal but higher. So the circuit equalized, but is maintaining a higher pressure than the other chillers. Non-condensables is where my mind goes. Yeah, when you get a situation like that where the standing pressures are higher for some reason, unless that chiller has more direct sunlight at that particular time, maybe it's at the end. Okay, so let me, this is for Al Iraqi. Sorry if not. So one of the places my mind goes in a circumstance like that, it's either non-condensables causing elevated pressures. That would be one possibility. Or if we've got these 3 chillers sitting side by side, okay, and our sun is over here on this side, right? This chiller here, especially from a side profile, is going to be blasted with all that radiant heat. And these over here very well could be just sitting in the shade, right? So all this is shaded. So these aren't dealing with direct sun. Like the top of the chiller deck, yeah, that is absolutely. But even inside of the chiller, like if it's multi-circuit, you could have this circuit is running at higher pressure or is hot, and this one is in the shade and it's not, right? And this also means this whole half of the chiller is this particular circuit's condenser, where this half of the chiller is the other circuit's condenser and it's in the shade. So you may, like, I don't know, but if it wasn't a if it wasn't a non-condensables issue, it could just be where the sun is at when you're looking at it. And with all of them off and the sun is, say, more focused on one particular machine than the others, and the others are in the shade, and this one's receiving a lot of radiant heat, then that could be causing the pressures to rise and elevate a bit compared to these others, where these others would be equalized more to just ambient temperature. This one is likely to be a little higher than ambient, which is why, like when we're doing say you do a saturation check on a refrigerant circuit. So one of the ways we can do that, recover a good portion of the charge, for example, or the majority of the charge, and put it into a recovery cylinder and have it sit for a minute and kind of settle. Now, what's important when you do this is don't let it sit in the sunlight. It has to sit in a shady spot that is equalized to ambient. That's important because if you let it sit in the sun, or if it's got hot air pushing onto it from something else, that's going to raise that tank's temperature, and it's going to cause that refrigerant to show a higher pressure, and you could get a false non-condensable reading. Whereas when if there's non-condensables in that refrigerant, when you put it into that tank and let it kind of settle out for a bit, you'll see that that tank has a much higher pressure than ambient saturation for that refrigerant. So if we have a saturation of 100, if it's 100 degrees outside, then we would expect that refrigerant to be at a 100 degrees saturated temperature once it has settled and it's had time in the shade. You go roll that same cylinder out in the sun, after a few minutes, you're going to artificially cause a higher saturation pressure, and it has nothing to do with non-condensables. So I would expect you'd have a similar possible concept here, where it may just be the location of where the radiant heat is being focused and where it's not. That's something you could look at or consider. Yeah, dude, nothing works. You think of how a grocery store or any other major store works. Yes. Oh, yeah. I mean, it's true. Yeah, and that's not even talking about their refrigeration equipment for the cold side. Yeah, grocery stores and stuff have data racks. Absolutely, they have to, because of. I mean, you think about it. They've got all those cash registers. They've got their whole processing or inventory system for the store. Like, there's a lot of data and bandwidth passing through one grocery store. Absolutely. How are the pressures in operation? So, well, doctor, I need a little more information than that in terms of what pressures, type of machine, refrigerant, like I need a little more than that to be able to give a response. It's just a little too broad for me to effectively say anything meaningful. I imagine that it's like water cooling a standard PC unit, water blocks on, right, yes. Problem though is taking condensation if the components get too cold. Right, well that comes back to the humidity control in addition to temperature control, right? Like there's very strict balances to that. And that chiller techs tend to struggle when it comes to what comes after the chiller, i.e. the hydronic loop terminals. Yeah, exactly. Well, and that's one of that goes back to like some of my course ideas, right? In my certification course, I very heavily talk about the rest of the system outside of just the chiller. But I don't get into the air handlers and terminal units. Like that's something, that would be just going too far, right? That wasn't the scope of the course material, but it was the whole plant as a whole was, right? So I cover the entire plant without. But once we go into the actual load in space, that's where I kind of chop things off. And I did that out of necessity, because if I went into the terminal systems, I mean, it'd add a lot to the course if I was to do that the way that I would do it. So that's where I go back to having a similar to the certification course, but heavy commercial focused, right? So DX and terminal units, things of that nature, and really honing in, static pressure controls, fan power boxes, VAVs, balancing outside air units and systems and makeup air. Like, there's this whole side of this world that I haven't got to build any material for yet. That's what I'm thinking about when I think about that course, right? And you're absolutely right. For guys who strictly train up on chillers, it can be really difficult to then expand beyond, okay, what happens outside of this? And it has everything to do with why we're trying to control the chiller where we are. What happens outside of the chiller has everything to do with what our set point is and why we need a particular set point and what we could do with those points in order to affect what happens at the chiller, right? They're not disconnected from each other. They're absolutely a cohesive ecosystem, but it is not something that we typically think of in that way. Or an organism. Maybe you think of it as an organism. Gotta check the oil submerged PC builds. They're wild. Yeah. Taking a serious course and all that, especially the hydronics and all that relates to water flow pumps and yeah. How does Michael Jackson measure tonnage? Oh Lord. I don't know. I'm not even going to try. Right, key proper dew point. Use. Well, really. Exactly my thought. Liquid cooling thing, measured server components. Well, and I think one thing, like our density, so that's one of the issues we have with modern server racks. We have a limitation on how dense we can pack those racks into a particular, or the servers into a rack, because we have to provide space for the air circulation and everything else. And we also get back into just the climate control aspect of it. Now think about it from a perspective of the whole data center is liquid submerged cooling. We no longer have the climate control problems, right? It's more about controlling the temperature in that solution, not necessarily being as worried about the climate of the entire space. And because of that, because we have physical liquid making contact, our density that we can stack those servers into alongside of each other becomes much smaller. We can get way more servers closer together in these vats than what we could do in an air-cooled rack with current designs. And so, like, I can just see how there's just so many incentives to really get that technology right. And again, from us on a hydronic perspective, just flow that through an isolation heat exchanger and we're back to the races. We cool their solution, but we keep our treated water in our chiller, and that way if we need to open things, drain things, like, we're not affecting their expensive solution that they flow through their servers. We're just affecting our regular chilled water system and whatever heat exchangers we're using in the process. I think it's just such a good direction to go. Like, the more you think through the benefits of it, like, it's just, I'm done. Usually you don't get to learn this stuff until you see it in the, exactly. Hopefully it was right. Yeah, well, that's the issue I have, right? And that's the issue we've had with chillers too. Like, it's sure we have manuals at least with chillers, but it's difficult to learn this stuff until you're just in front of it, which is hence why Chiller Academy became a thing, you know? I am solving that problem. They have to use a dehumidifier on top of the liquid cooling as well. Man, right. Just well, but yeah, it comes back to we've got to protect those electronics. So yeah, yep. They're dehumidifying. Yeah, you're right. Yeah, Michael's right there. Be really hard to get very low dew point. Also having a low temp overall dry. Yep. Yes. My condenser approach is relatively high. 8 degrees Celsius. Whew, even after mechanical brushing chillers. YK chiller. Okay, so you've got damn, your approach is through the roof. Is as usual. Constant speed pump. All right, so you're happy with the GPM? Yeah, 2 degrees. Yes, it should be 2 degrees Celsius. We have not verified it because the pipe. We do not. I've not seen these kinds of pumps, and would right. Okay. High approach outside of. So you've got clean tubes. I'm assuming none of your tubes are plugged. So that would be one question there, Shrek, is do you have any plugged tubes or are they all open? I know you've brushed them, but are there any that have been condemned and plugged on either end? And I'm assuming that when you brush them, you were able to push the brush through all the tubes. You didn't have any blocked tubes in the process. So because either blocked tubes or plugged tubes, once you don't get very far, you don't get very many of those before you start having major impact. Now, I'll continue with. Now, Michael, be careful there. So when you're doing the conversion, you have to convert not 8 degrees to Fahrenheit. It's not quite that simple of a conversion. It would be, I would expect that to be, they've got like in the teens of approach, teens to 20s, if you did that conversion properly. Anyway, just be careful when you're converting Celsius to Fahrenheit when you're talking about Celsius differential compared to physical temperature. Anyway, I've learned that the hard way. That's why I'm saying that. Non-condensables. So Shrek, non-condensables would be one of the big things I'm looking at, or an overcharge, right? So if you have an overcharge, you're stacking too much in the condenser, that's going to cause approach to elevate. If you said yes, yeah, okay, there we go. All right, yeah. So non-condensables is the big thing I'm really worried about there, or an overcharge possibly. So like the liquid in the condenser, in terms of a refrigerant perspective, is usually about 1/3 to at max 1/2 sight glass on those machines. If you're seeing above that in terms of liquid, and say you're up towards the top of the sight glass or above, way too much liquid stacking in the condenser. We need to figure out, whether it's a metering valve issue, whether it's the liquid level sensor issue. That'd be one thing that could cause elevated approach. Now, but more than likely, it's a non-condensables issue. However it happened, at some point, it doesn't really matter. We just got to get them out of there, which that depends on your site, what you have available to you. The simplest version of that's okay with the EPA is remove the refrigerant, pull a fresh evacuation, make sure the machine's tight, get everything out, and then just go back with brand new charge. That's the most EPA centric version. The alternatives would be trying to get those non-condensables to consolidate and bleed them off, but you can't do that with a machine online. So that's something to keep in mind is when the machine is running. So let's say this is our condenser. that machine has a baffled up here up top that our discharge line connects to, and then all of our gases hit and kind of dissipate over that baffling. But your non-condensables will usually collect about mid condenser in this zone. So even if your machine is running and you tried to purge non-condensables, you're purging just refrigerant with it on. This is ineffective. The only time these non-condensables are going to stack up here is when the machine is off, so bear that in mind. Now, that's the thing, though. It's not possible for you to purge this without purging refrigerant with it. So I cannot legally recommend you try to do a purge method. So now, maybe you could get a portable purge. So like RefTech, for example, RefTech makes portable purges. Now they're usually, I'd have to look at the specifications. Those are meant for low pressure machines. 134A is a high pressure machine. So I don't know that if they will work on high pressure equipment. I'd have to look that up on RefTech's design parameters for their purge units. But if they could, that would be one option you'd have. To do that, I would have the machine off. You would connect one hose to this port of your connect one hose to this port to the top port of your condenser. Now you've got a couple of ports on your YKs. You've got a much larger one, you've got some smaller ones. So one would connect to one port, you'd connect the drain off of the purge to another port, and then you would run the purge unit to eventually get all those non-condensables out, right? That's one way to get them out without having to completely replace the charge. So yeah, after brushing, I get down to 4 to 5. That's still pretty high. So yeah, you very likely had a combination there. Yeah, half full sight glass. That's perfectly fine. You gotta go through the Freedom Unit. Hey, you know, Sterling, I've done enough international stuff at this point. I'm starting to get a handle on it. I'm trying to, at least. You know, I still got some practice. But what's the best? Yeah, to get the yeah. So we try bleeding the air, brushing. That's really all you have. You could try to like I said, I'm not a fan of the whole purge aspects. Not a fan of doing the purge method there, because you do end up losing. Like, even if I wasn't worried about the EPA issues and stuff, and like all the problems there, if I wouldn't want to lose that much refrigerant, because you're going to lose a lot of the chiller's refrigerant just trying to do a vent purge like this. That's a major issue I have. We have too much refrigerant in there. It's too expensive. Like, it's just, no. I don't like that method. So that's where I go to either replace the charge, which is very unfortunate, or if we can get a purge unit to do that, which I guess I could look up really fast. I have to use these kind of purge units they sell here. Yeah, I don't really want to take out, yeah, exactly. I agree. Yeah, that's a lot of refrigerant. So I'm going to go to RefTech's website. All right, so let's go to website. We're going to, come on, product categories. Let's see, equipment, pumps, videos, purge system. So they have that. They have the mini purge, portable high speed. Okay, perfect. Okay, so the mini purge can do both. All right, so this is exactly what I'm talking about right here. You can get the little mini purge, and unit temporarily connects with high, low pressure refrigerant, rapidly get non-condensables. let's see. I want to be very cautious that. All right, so they say that it's compatible with high pressure. They don't give any like numbers or specifications. I can get you in touch with them, or you can just reach out to them yourself. RefTech is an amazing company. Highly support them. Highly recommend them. So it's just in terms of their service area compared to where you are. I don't know that part, but I do know that they're great guys. I'd really recommend working with them. And that's probably your best solution in a scenario like this is get that little mini purge, the little portable purge that they sell, and you're going to connect that, and that purge will get those non-condensables out of there. It's going to take some time, especially with as bad as they sound like they are for your machine. It's important for us to understand where that non-condensables came from, but first things first, we can try to just try to get the non-condensables out of there in the first place. Because here's the other thing. You don't want to leave them in there too much because those non-condensables and the moisture that they bring with them, right? So now when we get into this scenario, we're dealing with more than just non-condensables. We're also dealing with possible moisture issues, which is where your filter dryers come in. For a YK, that's going to be your eductor dryer. So you have to make sure that we're changing those eductor dryers out so that we can get. That's where the moisture, the water that gets caught or drawn in from the non-condenser, from the atmosphere, right? That's where that's coming in from. So, and I don't know if you just did a recent service on this machine, it's possible mistakes happen. It could be just pure nitrogen that accidentally got trapped somewhere and left in the system. It could be actual atmosphere that got drawn in. Now, atmosphere means mostly nitrogen. And there's also going to be moisture and H2O and water, in there. So that water will eventually condense in the chiller, and that'll get trapped in the evaporator specifically. So that'll get drawn into the eductor line because in terms of specific gravity, our 134 is heavier than water and our oil. So the oil and water will sit on top of the 134. So what we have to do is we have to get that off of the top of there. Well, our eductor system is actually built for that purpose, right? And that's why we have a filter dryer on the chiller's eductor so that whatever moisture and water is in there, it'll get caught there. And the purge unit will process whatever non-condensables have gotten trapped in the system as well. So say I do recovery, but how do I separate the non-condensables? Yeah, so that comes back to the purge. The only way we're going to truly get the non-condensables out without losing a lot of good refrigerant in the process is a purge unit. And you can do that on a recovery cylinder. So the way you would do that is, here, I need to wrap this up, but I'll just draw it real fast. So say you did have some refrigerant that you recovered and it had non-condensables in it. Now, I'll just plug before I close here. I do have a hands-on service class I'm doing in Houston, Texas, the first week of November 3rd through the 6th. So these are the exact processes and things. I'm going to physically show you how to hook up and what you can expect through this process, doing moisture removal, doing non-condensable removals, that whole process. Like, we're going to be doing the hands-on for this in Houston, Texas. If you want to get in on that, I've only got a few seats left. So you just need to email me at hvactime@hvactimetx.com. Send me an email. Let me know if the seats fill up. I do plan to do more of these next year. But if you're looking to get in on that, just throwing it out there. So this is exactly what the kind of stuff we're going to be doing in the class. So you've got a tank that has non-condensables in it, and so those are going to be trapped up here on the top. Now, our tank is going to have a vapor port, and then we'll have a liquid port, right? So part of what we would do is our recovery or our purge unit. Now, the purge unit has to sit up above the tank, right? So elevation matters because we're going to have a natural drain effect happening. But essentially, we're going to pull vapor off of the vapor line, because that's going to be getting the non-condensables specifically into the purge assembly. The purge assembly is going to then process that vapor, separate the non-condensables from the refrigerant, and then allow that liquid refrigerant that condenses to drain out and then drain back into, you could put it back into the liquid port of your cylinder. And you do this process, and this purge unit on your refrigerant tank can process those non-condensables. Now, it's not processing your moisture. So if you have a moisture problem, there's a different solution for that. And we have to configure things differently and use some filter dryers to get the moisture out of the system. But in terms of a in terms of getting non-condensables out of a cylinder with a purge unit, that would be the basic process and setup. Let's see. I'm just imagining some guy who worked on it before you. Yeah. I think it happened after some maintenance. We replaced the liquid line valve. Yep. I mean, it happens, right? If we know, as long as we can know why it happened, or we have an idea to prevent it from continuing, we're good, right? Other than that, it's there. Let's just fix it. That's the main focus, right? I'm afraid 0 bar seems. Off I go. Someone tried to pressure test. Yeah, push nitrogen. Yeah. Yeah, there's all kinds of ways accidents happen, right? As long as we just know it's not going to continue to happen, the main goal is just, let's fix it. Let's get the machine where it needs to be. Yeah, nobody wastes time. So you're in Estonia. Yeah, okay, I see. How do you rig suction? Keep the angle pull with not jerking down when free. YK, how do you rig a suction elbow off and keep the... Oh, yeah. I can add that. I can't get to any more questions today, but I am taking your question now. I'm adding it to my list. All right, it is added. I will get to your question there, Ray. I do not have time to do that today. What time zone will it be? If I can make it. Okay, so this class is not remote, so it's not a Zoom or Teams or anything like that. This is a in-person. I mean, when I say this, is whoever's attending, I won't be streaming this class or anything of that nature. This will be a live in-person, as in you will be sitting in the classroom with me. We will be doing these hands-ons together. My whole lab setups and all that I've got going on, like, we are going to be in the same room doing this. So Sterling, if you can make it across the pond and join us, that'd be awesome. But I know that's a long trip for just 4 days worth of a class. But that's what it will be. I do not plan to record and publish this class later in any way. Like, this is you're either there in person, or you'll just have to wait till another opportunity down the road, kind of thing. With that, I gotta go, guys. I appreciate y'all very much. Really enjoyed hanging out. MTT, make the time for your family, for your spouse, for your kids. They really need you. It's a crazy industry. We're always very busy. But if we don't make the time for them, there's just not going to be the time. And there's never going to be just perfect time. We have to make it. We have to be intentional with it. Please just keep that in mind as we go. With that,